All right, so what is a stack pointer upper limit? Okay, before that, okay, in the previous class, okay, we already defined the, okay, in the previous class, okay, you already learned about the stack, which in order to use a stack, you need to initialize your stack anywhere in your RAM, okay? So in order to use the stack, you need to initialize your stack pointer so that your stack pointer is pointed inside of your RAM. So in MVR, the stack can as big as its RAM. Okay, so the size of the stack is depending on your RAM size. Okay, if your RAM size is 2 kilobyte, then the size of the stack is 2 kilobyte as well. So note that we must not define the stack in the GPR nor in the IO memory. Okay, you recall back. Okay, this is your data memory. Okay, data memory can be divided in 3 parts. You have a GPR, IO, and RAM. So you cannot initialize your stack so that your stack inside of this GPR nor IO register. So the stack only can be inside of your RAM. So the stack pointer must be set to point above of this 0x60. Why need to point why you need to initialize your stack pointer so that the stack pointer is beyond this memory address? Because the starting address of your RAM, okay, if you recall it correctly, the starting address of your RAM here is starting at 00060, and then it is until 085F. So this is the memory address of your RAM, which is starting from 60 until 085F. So stack content is important as it used to store information when we're calling a subroutine. So another function why we're going to use the stack is we need to use it whenever you use the subroutine. Okay, so every time you use the subroutine, you need to use a stack. So the stack overflow will occur when the content of the stack is exceeded the upper limit. So the upper limit for the Atmega 32 is 0060. If the stack, okay, if you push a data, okay, below this address here, what happened? Then the stack overflow occurs. So that's why lah. Okay, so that's why we're going to initialize the stack so that the stack pointer point to RAM end. Okay, that is the reason because we're going to overcome this stack overflow. All right. So let's look at the subroutine. So this is another function lah. Okay, why you're going to learn about stack? Because in subroutine, okay, in order to use a subroutine, you need to initialize your stack pointer. So what is subroutine? So a subroutine is actually a sequence. Okay, so it's a sequence. Sorry. Okay, so a subroutine is a sequence of usually a consecutive instruction that carry out a single specific function or a number of a related function needed by calling a program. Okay, if you're going to call a program over and over and over, why not you use a subroutine? Okay, means that you no need to writing the same program over and over in order to do the same function or the same process. Okay, so a subroutine can be called from one or more location in a program. So actually, okay, this subroutine here is a slightly different from branch or jump instruction that you learned in the previous module. Okay, branch or jump instruction never come back to the place or to the next instruction after the jump happen. Okay, every time you do the jumping or you do the branching, so it will never return back, okay, to the place or to the next instruction after you do that jump instruction. But for subroutine, once it's go to the subroutine, and finish the subroutine task, then what happens is it will go back to the place or to the next instruction after you call that subroutine. Okay, so you see here. So this is your program. Okay, and then somehow here you call a subroutine. So what happens here? It will go to this subroutine, do the task inside the subroutine, and then after that, after it finished the task inside the subroutine, and it will return back to the next instruction just after you call that subroutine. So that is the difference between subroutine and branch or jump. Okay, why subroutine? Okay, to use the same set of instruction repeatedly. Okay, so every time you're going to use the same program, the same instruction, or the same task repeatedly, so it is advised for you to use the subroutine. Okay, so the subroutine, okay, it has two instructions. Okay, one we call it as a call instruction, and the other one we call it as a RTT instruction. Okay, let's look at the call instruction. So what happens when you do the call instruction? Okay, when a call subroutine is executed or is called, okay, the processor first save the address of the instruction just below the call instruction onto the stack, and then transfer control to the subroutine. So every time you call a subroutine, okay, means that you're going to jump to the subroutine. What happened here is, okay, the program counter, okay, will take the address, okay, of the next instruction, which is this instruction here. It will take the address here and put it, okay, inside of your stack. Okay, then after that, it will go to, or it will jump to this subroutine. Okay, so this is what happens every time you do the call instruction. Okay, so let's look at the call instruction. Okay, so the syntax of the call instruction. So this is a call instruction is a CA. Okay, so call instruction is a long call to subroutine. So it calls to a subroutine within the entire program of your memory. Okay, so the return address or to the instruction after the call will be stored onto the stack. So every time you use the call instruction, then what happens is the next address, the address of the next instruction will be stored to the stack. So that, after you finish your subroutine, then it will turn back to that instruction. So this is the syntax called K. K is your addresses, okay, and this is the operation, okay, which is it put K, okay, the address of the K to the program counter, and then the program counter now will go to that location. Okay, so let's look at the examples here. Okay, so this one here, okay, first line here, you move R16 to, okay, R0 to R16, and then suddenly, okay, you call check. So what happened here? Okay, now you're going to jump to this check here. Okay, before you jump to this checks here, what happened is, okay, you need, okay, the CPU will take the address. Okay, let's say like this is a 003, this address here, and then store it inside of your inside of your stack, and then after that it will go to this subroutine. Okay, so then you do the subroutine, and then every time it's, okay, it's execute the RET, means that you're going to return from subroutine. What happens when you return from the subroutine? So this address here that we earlier stored in the stack, the CPU will retrieve back this address, put it to your program counter, and then the program counter now know that now we're going to return to this address. So next what happens, it will return to this address and do this NOP instruction. Okay, so next, the second instruction here you need to know every time you use the subroutine is RET instruction. So what did this RET instruction do? So when the execution of the function is finished, so after you finish all the subroutine tasks, the RET instruction at the end of the subroutine is executed. Okay, so to exit from subroutine, you need to use the RET instruction. Okay, so what happened here? The address of the instruction below the call is loaded into the PC. Okay, so the address that you store inside your stack will be loaded to your program counter, and then the instruction below the call instruction is executed. Okay, once the program counter get the address, okay, from your stack, okay, now it knows that it's going to return back to this location. Okay, then what happened? Then after that, it will execute this instruction just after you do the call instruction. Okay, so this is the RET instruction. Okay, so RET is a return from subroutine. Okay, you're going to return address. What happened here? The return address is loaded from the stack. Every time you execute this RET instruction, the address you store in the stack will be loaded to your program counter. Then the program counter know that you're going to return to the location after you call the subroutine. So this is the syntax RET, and this is the operation. Okay, so this is similar to what I mentioned earlier. Okay, which is every time you execute this RET, what happened here is, okay, you're going to return from the subroutine, and then the CPU will take the address from the stack, put it to your program counter, and after that, you will go, the CPU will go to this location here, okay, and then execute this instruction NOP. Okay, so now we're going to look what is the role of stack in the subroutine. Okay, so this stack here is used to temporarily store address when the CPU execute the call instruction. So this is where the stack is used inside of the subroutine. Means that you're going to temporarily store the address every time the call instruction is executed. Okay, so this is how the CPU know where to resume when it returns from the call subroutine. Okay, hence we must very careful when manipulating the stack content. So every time you're going to manipulate the stack content, make sure that you need to take extra careful. Okay, because somehow if you use the stack randomly. So what happened here is then for some reason you cannot return back from your subroutine. Okay, so for AVR whose program counter is no longer than 60-bit, okay, for example, for Amiga 32, the value of the program counter can be broken into 2 bytes, which is the lower byte is pushed on the stack first and the higher byte is pushed. Okay, so this one here, okay, so this one here we use as a little Indian. Okay, we call it as a little Indian. Okay, actually, Indian, okay, we have 2 types. Okay, one is a big Indian, and the second one we call it as a little Indian. Okay, so what are the difference between big Indian and little Indian? Okay, so this Indian is how you're going to store an address or how you're going to store a data inside of your memory. Okay, so if you use the little Indian, okay, so this is your memory address. Okay, so this is your, for example, this is your RAM. Okay, 085S, and this one here you have a 085E, and this is a 085D, and this one is 085C. Okay, so let's look here. what are the difference if you choose, okay, between the big Indian and little Indian. Okay, how the data will be, or how the address will, okay, will be stored to your RAM here. Okay, next you have a data, okay, a 60-bit data, which is something like 7A16, for example. So this is your data. Okay. So now you're going to store this data, 16-bit data, to your memory address. Okay, to your data memory or to your RAM. In this case here, below here, this is your RAM. Okay, this is your data memory. Okay, since this data here is a 16-bit, okay, so you can divide it into 2 bytes. One is a low byte, and the second one is a high byte. Okay, so now if you use the little Indian, what happened here is, okay, so this is a little Indian and this is a big Indian. So we are going to see the difference, how the data, okay, how this data or this memory will be stored inside of your data memory. Okay, for example, if you use the little Indian, okay, what happened here? The lower byte will be stored to your data memory first, and after that, followed by the higher byte. In this case here, the lower byte is pushed to the stack, and then the higher byte is pushed. So what happened? 16 will be stored in the location of 085F, and then followed by 7A. Okay, this is why by using the little Indian lah. Okay, is if that CPU or if that processor is used a big Indian, so what happened here is the higher byte will be stored to the stack first, and then followed by the lower byte. So in this case here, 7A will be stored to this location and followed by 16. So for ArcMega 32, okay, for AVR Studio ArcMega 32, it used the little Indian, means that it will store the lower byte followed by higher byte. If you use other compiler or other software, okay, some of the software might use the big Indian and some of the software might use, or some of the compiler might use the little Indian. But for AVR Studio, okay, it will use this little Indian to store a data inside of your data memory. Okay, so in this class, we're focusing on the little Indian, okay, to store a data to data memory. Okay, this is only valid for the data that is bigger than 8-bit lah. For data that is 8-bit, no problem. If the data is greater than 8-bit, which is 16-bit, 32-bit, then you need to make sure that you store the lowest first to your memory, followed by the highest, and etc. Okay, so for AVR whose program counter is longer than 60-bit, okay, but shorter than 24-bit, the value of the program counter is broken up to 3 bytes. Okay, so if you have a 24-bit, so what are you going to do? Okay, you need to divide it to 3 bytes lah. Okay, so this is a 24-bit data. Okay, so what happened? You're going to divide it into 3 bytes. Okay, so this is the lowest, this is the highest, this is the middle. So what happened? You're going to put the lowest byte to your stack, followed by the middle byte, and then finally push the higher byte. Okay, any question up until here? This is how we going, okay, how you're going to save data, or you're going to save what we call here memory address to the program, to the data memory. Okay, so for IVR Studio ArcMega 32, we're going to use the little Indian. Okay, if no question, then we go to the next slide. Okay, so why use subroutine? Okay, so first, code reuse. Okay, means that you no longer need to write the same code over and over. Okay, you can simply use the code, just call the subroutine, and you can reuse the code over and over. Okay, easier to understand the code. Okay, because your code will small. Okay, the size of your code will be smaller compared if you write the whole program. Okay, without use the subroutine, and you can do the divide and conquer. So means that the complex tasks are easier when broken down into the smaller tasks. Okay, so this is the reason lah why we use the subroutine, and simplify the code in the debugging process. Also, in order to do some debugging process, so it will much simpler compared to if you not use the subroutine. So how does call subroutine in assembly? Okay, so what happened here? This is the okay. This is what happened, and example of the subroutine. So this is an example of subroutine lah. Okay, one of the easiest example that I can tell you is okay, if you're going to do the what we call here, if you're going to do a LED patterns. Okay, so you have a H LED, you're going to do the LED pattern such as a running lights, okay, blinking light. So every time you do the running light, you need to call a certain delay, okay, in order to make it blinking. So what you're going to do, okay, so we need to have a one subroutine that will create a certain delay. For example, if you have 8 LEDs, okay, so you're going to do a blinking pattern, okay, or a running light. Okay, so this is the first LED will turn on and the rest of the LED turn off. Okay, this is a sequence 1, this is a sequence 2, sequence 3. So this LED will turn on, the rest turn off. And then what happened here? Each of this blinking here, you need to have a 1 second delay. So if you write the program, okay, with a 1 second delay, okay, so what happened here? The program will longer. So since this 1 second delay, you call it repeatedly for the sequence number 2, sequence number 3, sequence number 4. Why not we make this 1 second delay as a subroutine? So you just call that 1 second delay subroutine to call the delay for each of this pattern here. Okay, so this sequence here. Okay, and then okay, a part of the call instruction, okay, it also have the rcall instruction. Okay, so rcall actually is similar to the rjump lah. Okay, previously we have the jump instruction, and then we have the rjump and ijump. Similar to this one here, okay, the call instruction also have a rcall and then icall. Okay, but most of the time we'll only use these two lah. Okay, the call instruction and jump instruction. Okay, so rcall is a repetitive call to a subroutine. Okay, so this is the syntax and this is the operation. And then after that, okay, so this is the what we call here the example by using the rcall. Okay, actually you can replace this rcall with a call instruction also can. Okay, and then we have the icall instruction. So this icall instruction is indirect call to subroutine. Okay, in which you're going to see the pointer register Z register in order to jump to that location. So this is the syntax icall, and this is the operation, and this is an example by using the icall. Okay, so icall here, what happened here? The call subroutine, okay, it will go to the subroutine that is pointed by your pointer register Z. Okay, so now let's look at the subroutine example and how this subroutine works. Okay, so write a program, okay, to count up from 00 to FF and send the count to port B. Okay, use a one call subroutine for sending the data to port B, and another one for time delay, put time delay between each issuing of data to port B. So means that you're going to write a program, okay, to do a counting sequence, and then at the same time send the data to port B. Okay, you're going to use a call subroutine in order to send the data to port B, and another subroutine, okay, to create a delay. So every time you send the data, you need to have a certain delay before the counting increase. Okay, so this is the what we call here. This is the program that you will write. Okay, started with this one here. Include the mt212.inc file, and then you define your R20 with a count. So every time you see the word count, you know that that is belong to R20, and then you origin your program at address 0. So that's why you see here your program here, all the instruction here, okay, all the of your programming here is started at location 0000 inside of your programmer memory. So this is your program memory address. Okay, so at address 00, you have this instruction here. Address 01, this is the instruction. 02, this is the instruction, and so forth. Okay, so let's look line by line here. What happened? Okay, so this the first 4 lines here. Okay, so this one here, what you're going to initialize your stack pointer. Okay, and then LDI count equal to 0 means that you're going to put 0 to your count, which is R20 equal to 0. And then you have a label back here, and then call display. So what happens when you have the call display? So, okay, I just draw your data memory. Okay, so this is your data memory. Okay, so this is address 085F, and this is a 5E. 085 D, and this is a 085 C, and this is a 085 B, and this is a 085A. Okay, so this one here, so what happened? Okay, you're going to initialize the stack pointer, so the stack pointer point to your RAM end. Okay, so this is your stack pointer. Okay, so currently your stack pointer point to your RAM end after you do this 4 instruction here, okay, to initialize your stack pointer. And then load I count with 0, so you're going to put R20 with 0. And then after that, call display. So what happened? When you call display means that you're going to jump to the subroutine display. Okay, subroutine name display. So before you go to that subroutine display, so what the CPU do here is the CPU, okay, will take this address and put it to your stack pointer. Okay, and put it to your stack. Okay, so now this is the address 0007, which is this address here is the next address after you call the display subroutine. Okay, so this is the instruction that you need to do lah after you exit from your subroutine. So what happened here? You divided this address to 2 bytes. One is low and one is high. Okay, so previously, okay, so what happened? Okay, so since here we are going to use the little Indian. Okay, so little Indian means that the little, okay, the lower byte will be pushed to the stack first and then followed by the higher byte. So what happened here is, okay, so since this is your address, okay, of the next instruction, so 07 will be stored to this location and then followed by 0, 0. What happened to your stack pointer? Then your stack pointer will point to this location after you store this address to your stacks. Okay, and then after that, what happened? Okay, it will jump to call display. So this is your call display. Okay, and then it will go this thing. It will do this thing: increment count, output bit count, call delay. And then you see here, you have another call delay instruction here. So what happened? The CPU will take this address. Okay, the next instruction address. Okay, every time you execute the call, what happened here is the PC, okay, the CPU will take this address here, okay, the next instruction address, put it to this stack. Okay, so the next instruction is address is 000C. So you divide it into low and high and put the low here first, 0C followed by 0, 0 to your stack. What about your stack pointer? Your stack pointer now point to this address 085B. Okay. And then what happened? Then it will jump to this location. Okay, to the delay subroutine. Okay, do the delay things, and after it finished, then it going to return. Okay, you see the RTT instruction. So what happened when the return instruction is executed? Okay, means that you're going to exit from subroutine and return to the location that you stopped before. Okay, so what happened here is the program counter, okay, will take the value from the stack. Okay, so this is your stack pointer, point to this address. So the program counter will take this value 0C00. Okay, so 0C00 load to the program counter. So now the CPU know that, okay, now we need to return to this location. Okay, 000C. Okay, so what happened? The program counter go to the location and then suddenly another return instruction is executed. So what happened? This instruction here, okay, so after you do the return and then the program counter now point to this address. Okay, after the first return, okay, and you take the CPU take this address, put to the program counter. What happened here is the stack pointer now incremented and point to this address 085D. Okay, then the program counter go to this location and see, okay, another return. So what happened here is, okay, the CPU, okay, will load this value to the program counter. Okay, now the program counter become 000C, 7. Okay, and then what about the stack pointer? Stack pointer will increment it and point to this address. Okay, and then so now the CPU know that, okay, program counter saying that now we need to go to this location 0007. So where is the 0007? So this is the 0007, and then do this instruction, which is R jump back. And what happened? It will go to this location back, call display, okay, and then the process will keep repeating. Okay, so this is what happened every time you call this, you use the call instruction and you use the RTT instruction, which is call instruction. You're going to jump to your subroutine, and then after you finish all the subroutine tasks, and then you need to return back, and okay, then RTT instruction is executed. Okay, so this is what happened. Okay, this is the summary what happened to the program above. Okay, so first you initialize your stack pointer so that your stack pointer point to your run end, and then after that, okay, after a call display, so what happened here? You take the value of, you take the address of the next instruction just before the call display, put it to your stack. Okay, and then your stack pointer is decremented and point to this address, and then another call delay. So what happened here? The CPU will take the next instruction address and put it on the stack, and the stack pointer is incremented. Decremented and point to this location. And then after you finish this delay subroutine, and then you're going to execute RET. So what happened here? This value here, 000C, will be loaded to your program counter, and the stack pointer now incremented, okay, pointed to this address. Okay, then you have another RET instruction. So what happened? This address is loaded to your program counter, and the stack pointer is incremented and point to this address. Okay, so this is what happened to the stack pointer every time you use the call and RET instruction. Okay, any question up until here? Ada soalan tak? Okay, if no soalan, if no question, then we'll look at this, what we call here, exercise or examples. Okay, given that, okay, you have a program here. Okay, so you're going to answer the following question with this assembly program below. Okay, you given the program here. Okay, so this is your program, and this is the address of the program. And then what you're going to do here is you're going to state the content of the following table after this assembly program is executed right after the instruction RET. Means that after you call the RET, then you stop. Okay, so the uppermost memory location is 085F. Okay, so this is the table. Okay, no tables here. Okay, so this is the table that you're going to fill up. Okay, you have a data memory. Okay, which is this is your stack lah. Okay. Okay, so this is 85F. Then you have a 85D E, 85D, okay, and then okay, so this is the table that you're going to fill in based on this program here. Okay, and then bear in mind that so you're going to state the content of the following table after the assembly program is executed right after the instruction RET. Means that after you execute the RET, then you stop. Okay, no need to run the whole program. Okay, after the RET execute, then you stop and fill in all these tables here. Okay, so what are you going to do? Okay, first you go line by lines lah. Okay, check line by lines what this program do. Okay, so the first 4 line here, what is this? LDI R60 high ramen out SPH R16 LDI R60 low ramen out SPL R16. So what is this actually? Can you tell me? What is this?
Initialize a stack pointer.
Okay, you're going to initialize the stack pointer so that your stack pointer point to your RAM end. Okay, so your RAM end is actually at 085F. Okay, so this is your stack pointer. Okay, the stack pointer will point to this address. Okay, after you perform Okay, this instruction here. Okay, then LDI R26 35. So what happened here? You're going to load 35 with R26. Okay, so we just put the 35. Okay, you cannot see it clearly. Okay, I change the color. Okay, so this is 35. Sorry. Can I change the color? Cannot. Okay, never mind. Okay, so this is 35. And then load I R27 89. So what happened here? Okay, you put 89 to R27. And then load I R28 48. So 48, you're going to put it to your R28. Okay, so this is the value that you load to this register here, and then you already finish execute until this instruction here. Okay, and then next, this line here, push R26. Okay, what happens when you push R26? Anyone? What happens when you push R26? Okay, you're going to store a data. Okay, put a data to your stack. Okay, what is the data came from? From R26. Okay, so you take 35 from R26 and put it to your stack pointer. Okay, what happened to your stack pointer? Stack pointer will be decremented by 1. Okay, so now your stack pointer point to this address. Okay, and then next, what are you going to do? Okay, next instruction, push R27. So what happened? Okay, you take R27 contents value and put it to your stack. So now your stack we have 89 and stack pointer is decremented by 1. And then push another one. Okay, push R28. So take 48, put it to your stack, and then stack pointer decremented by 1. So we already finished up until here. Any question up until here? Ada soalan tak sampai sini? Okay, and then next, call modify. Okay, so this is a call modify. So what happens when you call the modify? Means that you're going to jump to modify subroutine. Okay, before you go to the modify subroutine, what are you going to do?
Store the program counter.
Okay, and you need to store the next address of the next instruction. Okay, the next instruction address and put it to your stack. Okay, so the next instruction is pop R28. Take the address, okay, which is 030C. Okay, and then you can divide it to 2 bytes. This is a low and high. Okay, since we use the Little Endian, so 0C will be stored to your stack first, followed by 03. And what happened to your stack pointer? Stack pointer now point to this address 85A. Okay, then after that, then it will jump to this modify location. Okay, the modify subroutine. And do this thing STS 085D R27. So what happened when you execute this line? Anyone? STS 085D R27. What this instruction do?
Store the value
Yes.
89 to the location 85D.
Okay, so store the value from R27, which is 89, and put it to a location 85D. So 085D. So this is your 085D. Okay, now you store 89 inside here. Okay, so the value, the previous value will be rewrite lah with a new value, which is 89. Okay, then STS085E R28. Okay, the same thing here, which is you're going to store R28 value, which is 48, and put it to address 85E. So you go to 85E. Okay, so this address here, and store 48. Okay, and then next, ADD R28 R27. So what happened here? Okay, you're going to add R28 with R27 and put the result to R28. So what is R28? 48 plus with R27, 89. Press the calculator. What would be the result? What is the result here? Anyone?
D1.
Okay, D1. Okay, you get a D1. And this D1 here, you store in your R28. So R28 now no longer 48. It have the new value D1. Okay, next, RET. So what happened when RET? Okay, means that you're going to return from subroutine. Okay, what happened when you're going to return from the subroutine? The CPU will take this address 030C, put it to your program counter. Okay, so this address here 0C03, put it to your program counter. What happened to your stack pointer? Your stack pointer now will point to this address. After you retrieve the value, put it to your program counter. Now your program counter will increment it and point to this address. Okay, previously it point to 85A. Now it point to 85C. Okay, so this is your current stack pointer. Okay, do you need to do this pop instruction here? No need. Why no need? Because the question here asks you, okay, to stop right after you execute the RET. So you just stop here and update all the result. So what would be your program counter? Your program counter will be 030C. What is your stack pointer? Stack pointer now point to this address 085C. Okay, and what others? What about the others? Okay, the others just remain lah. Okay, so this is the answers that you get. R26 will have 35, 27, 89, 28 D1, and then program counter 030C, stack pointer is 085C, and then at this address here you have a 030C, 89, 48, and 35. Okay, then if you get the if your answer is correct, then you will get 10 marks. Okay, so this is the results. Any question? Okay, so if no question, then we go to another examples here for the stack pointer. Okay, so based on the program sequence below, find out the result of the affected register or a memory address. Assume the program has properly initialized the stack pointer to address 85F. The instructions are executed sequentially. Okay, then you get 10 marks. Okay, so this is the program here, and then you need to find out what are the value after you execute each of these instruction. Okay, so this is the given that this is the initial value. Okay, R16 0, R17 0, R18 also 0, R29 and R20 also 0. Stack pointer initialized to this address, and the stack content at 85F is 0, 0. Okay, so let's look at instruction number 1. Okay, LDI R16 5. What that instruction do?
The immediate value 5.
Okay, so you're going to load immediate 5 to R16. Now, R16 will have 0, 5. Okay, make sure that the answer must in hexadecimal. Okay, since this is a decimal, so you need to convert lah 5 to hexadecimal, and then it will be 0, 5. Okay, next. Simpan. Okay, so this is the label, simpan. Okay, why I call this is a label, you see here, this is a, you have a column here, and then push R16. So why? Okay, so why not we draw our stack? So this is your stack. Okay, every time you deal with a stack question, okay, make sure that you draw your stacks. Okay, so that you can keep trace what happened and keep trace your stack pointer location. Okay, so this is a 85F, 85E, D, 85C, 85B, and this is 858. Okay. Currently, stack pointer is initialized at this address 085F, and the stack content at this location here is 00. Okay, the value here is 00. Okay, push R16. So what happened? You're going to put R16 value, which is 5, to your stack. Okay, so what happened? Now this is become 05. What happened to your stack pointer? Stack pointer decremented by 1. Okay, and then decrement R16. So what happened when you do decrement R16? R16 now become 4. Okay, and then BRNE simpan. So what happened when BRNE simpan? Means that branch not equal. Okay, so now you're going to do the looping. Okay, if the R16 not equal to 0, then you will keep looping. Okay, do the loops here. If R16 equal to 0, then after that, you do the next instruction. Okay, since the R16 is 4, okay, what happened here? You go back to simpan, push R16. What is the current value of R16? 04. Put it to your program counter. What about the stack pointer? Stack pointer point to this address. Okay, decremented by 1. And decrement R16, R16 now become 3. Okay, branch not equal, yes, R16 is 3, not equal, go to simpan, push R16, 03, put there, and then decrement R16, R16 become 2. Okay, and then what happened to your stack pointer? Stack pointer is decremented by 1. Okay, and then branch not equal, yes, not equal because the R16 still have value 2. Go to simpan, push R16, so 02 you push here, stack pointer decremented by 1, and decrement R16, R16 become 1. Okay, branch not equal, yes, not equal, and then what happen? You go back to your simpan, push R16, 01 you put to your stack pointer now point to this address, and then push R16. Okay, we already did that. Decrement R16, R16 become 0. And what happened? When R16 becomes 0, then this one is invalid. Then you're going to do the next instruction. Okay, so what would be the answers that you need to put here? Okay, you need to put the current value lah of the of your R16 here. So this is R16 is 00. What about this one? Previously, before you do the 00, so this is of 01. And here, what is your stack pointer? Stack pointer point to this address 85A. Okay, so 0, sorry, not that column, not that box. Okay, 085A. Okay, what about here? Okay, so you see here at this location here. Okay, at this location 85B, you have 0Y. Okay, so you just 85P. Okay, then you have 0, 1. Okay, so this is the value that you need to put in this box here. What about the rest? Okay, no need to put lah. Okay, because the rest is same. Okay, then after that, okay, after the R60 equal to 0, and then this line here, this instruction, it become invalid, then it will exit from the loop and pop R17. So what happens when you pop R17? Okay, you're going to retrieve this value from the stack and put it to R17. What happened to your stack pointer? Stack pointer will incremented by 1. Okay, so now you just ni lah. Okay, R17. So what R70 value? 0, 1. Okay, pop R19. Okay, before that you need to put this. You need to update the stack pointer. So now stack pointer point to new address, which is 085B. Okay, pop R19. So what happened? This value here, 02. You're going to pop to R19. So what happened to your stack pointer? Stack pointer now incremented by 1. Okay, so now this one here, R19, will have 02. And what about your stack pointer? Stack pointer now point to address 85C. Okay, pop again. Okay, pop this value. Okay, put it to R18. Okay, what about the stack pointer? Stack pointer now increased by 1. So now a stack pointer point to address 085D. What about this one here? 03, you put it to R18. And last but not least, another pop R20. So what happened here? 04 from this location, from this stack, you're going to put it to R20. So 04, put it to R20. What about your stack pointer? Stack pointer increase by 1. So the current stack pointer value is 85. Okay, so you simply write 085. So this is the answer. Okay, any question about the stack pointer or module 8? Okay, we already finished the module 8. Any question?
Doctor, for
Yeah.
stack pointer, we store the program counter or not?
For the stack pointer, okay, the program counter is still updated. Okay, according